This mini recording is for Unit 1, Lesson 13 on inverse variation. So similar to direct variation and quadratic variation, and there are specific notes that I gave you for inverse variation, as complete with the equations that you'll use that are slightly different from the other two variations, and also with the graphing. Notice how the graph looks a little bit different. So make sure you've got your notes handy when you're working in this unit. But the equations for inverse variation, think of it as when x increases, y decreases by that same factor, and that same factor is k. So we're going to use f of x equals k divided by x, or y equals k divided by x. Again, f of x and y are the same value. They both represent the output, or the y values, and inputs are your x values. And it also helps to think of it as output varies inversely with the input. So your y values vary inversely with your x values. And specifically, if you're trying to find that constant value, you can rework these equations so that you're solving for k. So k equals x times y. Also think of it as k equals your input times your output. And just another look at another explanation about these graphs. Depending on what your k value is, it's going to determine where your graphs fall on your quadratic or on your coordinate plane. If the k value is positive, your graph will end up being in quadrant 1 and quadrant 3. And if your k value is negative, your graphs will fall in quadrant 2 and quadrant 4. So just pay attention to that. If k is positive, know it's going to be in these two quadrants. If k is negative, it will be in these two quadrants. And this type of graph is called a hyperbola. So there's two different arcs that don't intersect. So going through the process of determining an inverse variation is similar to what we've done with direct variation and quadratic variation. We're trying to determine in the table if there is a constant value, k. K is the constant. So k, we're going to use k equals x times y. So our x value, our input, times our output. So 1 times 20, we come out with 20 for this one. Looking at the second ordered pair, we have 2 times 10, that also equals 20. Third one, 4 times 5, we get a constant value of 20. 5 times 4, we get a constant value of 20, and 10 times 2, we get a constant value of 20. So for each of these, when we applied this constant equation, we got a value of k of being 20. So this one is an inverse variation. It's showing an inverse variation relationship because the constant value is the same for each ordered pair. Moving on to question number 2, when we want to look at the equation, we want our equation to look like y equals k k divided by x. So y equals k divided by x. So looking at this equation right here, we have x equals 3 times y. We want our y to be by itself. So I would first try rearranging this so that we're dividing by 3. So we end up with x divided by 3 equaling y. And we want to determine if that matches this equation. In this one, our x is in the numerator and we're dividing by a number. In our inverse variation equation, this would have to be a number divided by x, where x is in the denominator. So this one I would say is no, it is not an inverse variation relationship because the x is being as our main number and we're dividing by 3 with this one. Looking at question number 3 here, again, to determine if it matches our equation, get y by itself. So if I divide by x, those two cancel off. Dividing by x here, we're left with y equals negative 1 divided by x, and it should match our y equals a number divided by x, and it does. It's a number negative 1 divided by x. In our inverse variation equation, it should be a number divided by x. So this one is yes, it is an inverse variation relationship. We can also apply the inverse variation problems where we're told that there is an inverse variation and we have to determine a new value for a given value. So this is saying that y varies inversely with x. So I know that there's an inverse variation, so I can determine what the constant value is between this ordered pair when y equals 4 and x equals 2. So to find the constant, we're multiplying our input times our output. So k equals x times y, and in our problem, the x value is 2 and the y value is 4. So our constant for this inverse variation is when k equals 8. So we're going to use 8 for k to answer our next question. We want to determine y when x equals 16. So we already know it's an inverse variation. So we want to use our inverse variation equation, which is f of x equals k divided by x. And f of x and y are the same. They represent that same number. So we can also use y equals k divided by x. And we already found k to be 8. So y equals 8 divided by our x value 16. This means our y value will reduce to equal 1/2. So this is saying that when x equals 16 in this inverse variation, y is going to equal 1/2. And finally, we can also graph inverse variations. Remember, our graphs are going to be in 2 separate quadrants. So following these steps, we first want to figure out what the constant value is. We want to set up our inverse variation equation and then use the table of domain values, our inputs, to find our output, our y value, so that we can graph it. So if we first find k, we're multiplying our input times our output, so x times y. X is 2, y is 3. On this one, we find our constant value to equal 6. So the equation we're going to use to solve with these ordered pairs is y equals k, so 6 divided by x. And the reason why I put 6 there is we already found k to equal 6. So for this first one, our y equals 6 divided by our input, so 6 divided by negative 6, that comes out to be negative 1. Our second pair, 6 divided by a negative 3, we get negative 2. 6 divided by a negative 2, we get negative 3. Notice I'm using the same constant value, k, for this entire relation. 6 divided by negative 1, we get negative 6. 6 divided by 1 is 6. 6 divided by 2, we get 3. 6 divided by 3, we get 2. And 6 divided by 6, we get 1. So now we have our table of values. Each of these represents an ordered pair. And if we were to graph them, you would see that since k was positive, remember k equaled 6. Since k was positive, our graph had to be in this quadrant and in quadrant 3. And notice they will never intersect because they actually go on and on forever, and they get really, 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 really close to that y-axis, but they won't ever touch it. Same with that x-axis. As you graph it, they'll get really, really close to that x-axis, but they won't ever actually touch it.